you all are absolutely well. And today we will continue with a small topic that is related to the energy. So let's do that. Now, important thing what we have done last in the last 11th lecture was work done, right? Now, in this lecture, we will see a few things which are very, very important. Firstly, there is a thing called a Sankey diagram, right? What is Sankey diagram, first of all? Now, remember that when you're talking about a Sankey diagram, it's a representation. Because what happened actually in the last topic with the last class, we were doing conservation of energy, and I told you at that time that input energy is equal to output energy, or input power is equal to output power. How? That's what the point is. You can see here that whatever energy is being inputted can be go for the useful output energy, and also some of the energy will be wasted. So basically, Sankey diagram gives you an idea how the input energy will be distributed. It is distributed into useful energy output, and it is also distributed as the wasted energy. It can be multiple wasted energies as well. So basically what Sankey diagram is. Some Sankey diagram is a diagrammatical illustration of how the input energy transferred into the output energy. Definitely, some of the energy is transferred as a useful energy output, and some of the energy is wasted. But all of the total energy will be equal to the input energy, because the input energy equal to should be equal to the output energy. Both should be equal, right? Let's have an example here. You can see that, as I already told you, that inputted energy and output energy should be the same thing. Now, how? Let's have an example of a Sankey diagram. Now, Sankey diagram showing you a big two parallel lines in which you can see yourself. There are two Sankey diagrams, one for the normal bulb and one for the modern bulb. You can say a filament bulb, and one Sankey diagram is for the efficient. You can see that there is an input of 100 joules, right? And you can see these two arrows. One arrow shows that 75 joules of the energy is transferred as a radiation or as a light energy, out of which 25 joules of the energy is wasted. So they give you a proper diagrammatical illustration how the energy is distributed. On the other side, you can see that an inefficient, the old bulb, or the bulb which is not efficient, that is transferred as 90 joules of the energy is wasted, while 10 joules of the energy is just transferred. Now, at this point of time, we may think of it as an efficiency, which is our next topic. Before that, we will do power, and then we have efficiency. So, what is efficiency in that case? Outputted energy is 75 and inputted energy is 100 joules. Then, as a percentage, it will be 0.75 multiplied by 100. So, it will be 75% efficient system. On the other side, that system is 10% efficient system. So you can simply talk about it and you can simply discuss it, because that diagrammatical illustration tells you everything. After that, we have another very interesting topic, and that is what we called as power. We already talked about the work done. That is work done per unit time. So work done divided by time is power, right? Or energy transferred per unit time. The unit should be joules per second, but the SI unit is watts, right? So this is the power means altogether. Now, that is a question. We can talk about that. Calculate the energy transfer. The formula is what? P is equal to delta E or W, whatever, upon time. They say calculate the energy transfer. So delta E equal to PT. They're saying energy transferred when the iron with the power rating. Now, remember that power will always be provided in the form of a rating. And here it's given as 2000 watts. And time is given in 5 minutes. You have to convert that time into seconds by multiplying by 60. So 5 6 to 30, which is 300 seconds. So 2000 multiplied by 300. So it will be 6 1 2 3 on 2. Energy is joules. So this is the amount of energy transferred when the iron has a rating of 2000 watt and the time it takes is 5 minutes. Right? Now, the topic which we were talking about is definitely efficiency. What was efficiency? When you know how much energy is being used as a useful output and how much energy is being input. It's very simple. Efficiency is equal to useful energy output divided by total energy input. Or if you're talking about in the form of power, it will be useful power output divided by the total power output. Remember that numerator and denominator should be the same entities. If it's the energy, then denominator should be the energy. If numerator is power, denominator should be the power. But inputted power divided by outputted power divided by inputted power, outputted energy divided by inputted energy. It's always given in efficiency. There is no unit for efficiency. So you always multiply it by 100 to get the answer in percentage, right? Let's see a question so that you will understand what is meant by efficiency. An electric motor has an efficiency of 35. So efficiency is given as 35%. So you can change it by dividing it to 100, 0.35. It lifts a 7.2 kg load through a height of 5 meters in 3 seconds. Calculate the power of a motor. Now, power of a motor is definitely the inputted power. They're asking you why? Because you give power to the motor and that will be used to lift that load or all the things. Now, you can see that it lifts 7.2 kgs load to a height of 5. So technically, if there is a load, it should have a weight, right? And it is being lifted upward, which means potential energy. Energy divided by time will be power output. So what is the calculation for that? Power output is equal to potential energy, which is mgh divided by T. What is M? 7.2, G is 9.8, height is 5, and then you just divide it by 3 to get the value. So what exactly it is? 7.2 multiplied by 9.8 multiplied by 5 divided by 3, and it will be 117. So 117.5 watts, right? Is that the one? 0.6. Apologies. Now this is power output. So what is the formula? Efficiency equals to power output divided by power input. Now just put the values here, 0.35. Power output is given as 117.5. Inputted power is unknown, right? So very simple. You simply cross multiply that. So power input is equal to 117.5 divided by 0.35. So 117.5 divided by 0.35, and it will be 335.7. 335.71 volts. This is the inputted power which is given to the motor so that of power, right? So this is all we have done with work, power, energy, and work done. Now we have different type of energy resources, which we'll be going through. The biggest energy we have it is a sunlight. Right? Now, what exactly is sunlight? And on the basis of sunlight, there are different type of energies we have it, right? There are different equipments we use for the storage of the sun energy. But first of all, the important part is energy is being stored because the electromagnetic radiations are directly come from the sun, and most of our energy resources on the earth come indirectly from sun, right? So suns heat up the atmosphere, creating a wind and producing the waves. Water evaporated by the sun falls as a rain and filling up the reservoirs. What exactly I want to say that sun is somehow or another producing or indirectly is a cause of different type of energies on this world. But there are certain energies which has nothing to do with the sun. They have energy, they are energy resources on their own, like geothermal. It is basically due to the core of Earth, because it was said that for a very long period of time, the core of Earth is very hot. And due to that hotness of the core, there is a heat energy inside the Earth. And that energy is called as a geothermal. As the name suggests, geo means earth and thermal means heat. Then you have a nuclear energy. This comes from the element that makes up a small portion on the earth crust. Tidal energy, they but they are due to the gravitational attraction of the moon. Now, on the basis of sun, what are the things which we can use for different purposes for storing the energy? The best thing you can solar cell. Now, solar cell is a sort of a cell that stores the energy directly from the sun. So what happened? The radiation falls on it and it stores the energy that can be utilized once it stores the energy, right? So this is like that. The sunlight is falling on the solar cell and they store the energy, right, within them. And you can use those energy things, or you can use that energy city purposes for a small scale businesses. Okay. There are actually still working on the large scale thing. We actually have to work on this. So basically, what exactly are the benefits of? So basically, this is what the point is.